All right, we are live now. It looks like. Welcome, man of the hour, Kyle Gillett. How you doing tonight?
Pretty good, Gabe. How are you?
I'm doing freaking wonderful. Um, let's see here. Are we getting a little bit of feedback, maybe? Kyle, do you have the Discord stage event opened up?
I do not.
Okay. I'm picking up some vehicle noise in the background. Is there someone starting a car near you?
Yeah, let me try something here.
Okay, I was gonna say that's a hypersensitive mic. You're like ready to do some ASMR, man.
I'm surprised that it's that sensitive.
Yeah, I think
That's
you might want
crazy.
to turn your
Yeah, I'm
input
going
down
to.
just a little bit. That was like ASMR levels. I was pretty sure you were about to start doing mouth sounds into my ear.
That's
That's like
remarkable.
the
I don't know if we're gonna get that deep. This isn't gonna be that late into the night, but
bro. If you did like a whispered, like tapping and whispering while you did your storm relative helicity presentation, I think we actually might get an entirely new subset of female audience members
maybe
dropping in here. So
for the forecast videos, we'll just start reading the SPC outlooks like that, word for word.
maybe a little bit higher with the input volume, like just a tad bit higher.
Okay.
Let's try that real quick.
I'm running about 90%, so I could talk a little bit louder. So
No, that's perfect.
if that
Perfect
works.
right there.
Okay. Okay.
Beautiful. Yep,
Sweet.
beautiful. So, all right, people on Discord, I can see all of you guys in here right now. Kazaki, Bomber Fox, Chaser Mag. Awesome to have all of you in here. Gen Shark, Pezzex, WX, that's a weird one. Sorry if I pronounced that wrong. When are we getting the Gabe ASMR office hours? Do not, listen, I've done some crazy stuff already. Do not give me any wild ideas, guys. I might just do it. Mr. Steve 600, great to have you here. I'm going to go ahead and pop open the YouTube chat as well, so that way I can say hello to all of you wonderful folks over there. So, open up that bad boy. Give me just a second here. Perfect. Chat is popped out and ready to go. All right. So, folks, some of you, especially the people on Discord, probably know the drill by now. But for those who are hanging out on YouTube, these are a little bit different than our normal office hours Q&A sessions. There is a Q&A component at the end, but we are going to give one of our coaches, in this instance, it's Kyle Gillett, an opportunity to shine. He is going to give a full presentation, 10, 15, 20 minutes, something like that, on the topic of the night, which of course is storm relative helicity, something that we hear thrown around a whole lot. But there's a lot more that goes into it than just how high is the number when you're looking at the sounding. And so Kyle's really going to help to give you a fundamental understanding of what it is that goes into storm relative helicity, when you should be using it, and how it actually applies to severe weather forecasting. So that'll be coming up here in just a moment as we give people an opportunity to filter in before we start the presentation. And then I'll give a couple of updates about this, one more after the presentation, but we do have during the Q&A session an opportunity for all of our members to ask their questions. So on Discord, that means you'll need to sign up over there. Our moderators will drop some links in the chat for you guys to sign up for $3, and that gives you access to a bunch of perks. One of them is that you get to ask your questions. And then on YouTube, all you got to do is click that join button right underneath the video to join our channel membership, and you can ask questions as well. I'm going to start a Q&A over on YouTube, so you'll just click that Q&A button at the bottom, and your question will get thrown into the queue. And if you guys don't want to ask questions, you just want to hang out in the chat, you want to listen to the presentation and everything, that is totally fine as well. We really appreciate you being here with us tonight. So, Kyle, before we get started, I want to ask you, how has the storm chasing season been up there in the Northern Plains so far? I know we just got out of Central and Southern Plains season, and we're starting to really get into the time of year where that geographic area of the country starts to shine.
Yeah, I would say that my favorite time of year to chase up here is definitely kind of late July and into August. Some of my better chase days have actually been August. I'm up here in the Northern Plains, but so far this year, it's been pretty lackluster. I mean, there's a few days, more so in South Dakota, that had some decent storm structure, but I've actually only chased twice anywhere in the country this entire year because I've been busy with other stuff. But there have been quite a few severe weather events here in North Dakota that I have just completely sat out because the setup just has not looked very good. As busy as I am, a couple hours away, that's not really that big of a deal, right? That's pretty normal for us. But there just really hasn't been much of anything that's really got me too excited. And looking back, like a lot of the best stuff has been across the border up in Canada back in June and July, and the stuff that we've had here is just pretty generic, severe, nothing outstanding. Like kind of the most recent benchmarks for the Northern Plains have been like Mountain City or June 20th, the Enderlin Day, or like Gary, Watertowns, days like that. We haven't had anything that even approaches that caliber in any capacity so far this year. And there's a lot of August left. It does look like this pattern that we have in place right now, which has been kind of favorable, kind of not favorable. Depends on if we get certain parameters to kind of align. That looks to more than likely stick around. So we'll see how August goes. August is my favorite, but yeah, I think this year has been quite a letdown, especially compared to what we had last year.
Yeah, I think that's been a pretty much the prevailing sentiment across the storm chasing community, except for the very few who have managed to see some of the standouts in places like Illinois this year. It's just been definitely a little bit of a disappointing year from a storm chasing perspective.
Yeah, that's right. And there's definitely days where those are Illinois events or someplace else. There's a couple of events in like West Texas, New Mexico, where I'm like, I would have been nice to be there, but we just haven't had the signals that are like, yeah, for multiple days in a row, this looks good from a chasing perspective. Things can look good from a tornado perspective or a severe weather perspective, but it doesn't always mean that it's what you want for a storm chase, especially if you're like someone like myself. I chase for photography, and so I'm not just going to go out because there's tornado chances, right? I don't want grunge. I don't want it to be in the trees. I'm very particular about what I want, and that's been very detrimental to my chase success so far this year. But yeah, I mean, we've had a few good events. Every year is going to have some, but this year it's kind of been a hit and miss kind of thing where we have maybe a string of 5 events in a row that aren't very good, and then all of a sudden we'll end up with one that's not too bad. But yeah, compared to 2025, it's going to take a lot to compare with a year like that.
Hit or miss. I
Yeah,
guess they never miss, huh?
yeah,
You
that's
got a
right.
boyfriend. I bet. Does anyone get the? Do you get the reference?
It's familiar. It's from a song. If it's like pre 2000 or post 2000s, I have no idea. That's
It's one of the more famous TikTok trends of all time. Come on,
oh
Kyle. You're telling me you don't stay on top of that stuff?
yeah. See, no, I don't have a TikTok, so
You
I
got
get
it.
left behind with the new things. I'm feeling quite old these days, and I'm pretty sure there's a word for that, but I'm not gonna say it. I'll let
Well,
everybody else
I'll,
in the
I'll
chat
tell you
cook me
this,
here.
guys. Kyle is telling no lies because when we were actually formulating the forecast show, I remember the only concern you had was what time will we be doing this because I go to bed early. I'm an old man. So.
Yeah, yep, that's right. That's right.
All right. Well, all of you wonderful folks, give a couple more shout outs on YouTube. Zhao Sex, I hope I said that correctly, and Caleb WX. Great to have you guys here and chatting over on YouTube. And then on Discord, just more regulars. Awesome to have you folks back. Viper, Nebraska Chaser. See, we've got JM. You can't hide from me changing your username to JM. I know that means Sanus Northeast Chaser. Welcome back. Haven't seen you in a week or so, my friend. Atlas, and Ryan also here as well. Awesome. And Leo Moroni, 2026 is ass. Somebody actually called you out in 4K, Kyle, with one of your tweets.
Yeah,
So
that's yeah, that was after a severe weather event. Oh gosh, what was that? I don't remember, but yes, it was terrible. And at that point I was quite frustrated with the year, and I'm still at that point. I was just trying to find a nicer way to say it here for everybody, but yeah, that's my real opinion, I guess, of the year right there.
awesome. Well, I guess I appreciate the attempt to moderate yourself.
Yeah.
And with that, we'll go ahead and switch over into presentation mode. Seems like we've got a nice group of folks here who are ready to watch you present about storm relative felicity. So my
Mhm.
microphone is off and my camera is off as well. You have the floor, sir.
All right. So Hopefully, you guys can all see my shared screen here. And so thanks a lot, Gabe, for the intro, and thanks everybody for hopping on and listening to me ramble about this. This is gonna be a short presentation on storm relative helicity and kind of focusing on what it is, what goes into its calculation, and how we might interpret it for our storm forecasting um, utilities. Now, this is a parameter that a lot of people are probably familiar with. You've probably used it yourself. And in general, the way it's designed is essentially just to tell us, do we have the shear in place to help support supercells? And if you really think about it in that sense, this parameter is designed the correct way to attack that. However, especially when you start looking at things maybe from a little bit more of a storm chase perspective, um, SRH is a little bit more nuanced, and we'll talk about that in more details in just a moment. So this is what is and how to use storm relative helicity. So we're just going to call this SRH, or storm relative helicity. And essentially what this is, and this is actually defined by the SPC as a measure of the potential for cyclonic updraft rotation in right-moving supercells, and is typically calculated for the lowest 1 or 3 kilometers above the ground or within what's called the effective inflow layer. And that's defined by a certain amount of CAPE and a certain amount of SYN and all that stuff. So we're not going to go too much into effective inflow layer, but you might see that sometimes that'll be called ESRH, or effective SRH. And so what we're talking about here is helicity, which is just a measure of rotation, more or less. So you kind of think of it similar to vorticity for the sake of this conversation. And then the storm relative part means we're going to be taking into account the wind as far as the storm is concerned. And so when I say something about storm relative, you can consider this as car relative. Okay, so imagine you're going down the highway and you're in a car, right? You put your hand out the window and there's a wind that's coming at the front of the car, and you can feel it kind of blowing your hand back, right? That's not what the actual wind is on the highway, but that's the wind you feel because you're driving down the highway. So you could call that a car relative wind. That is the wind relative to the car's motion. And in this case, the storm, because it is moving through that wind, it also is going to be feeling some type of wind. So that's where the storm relative component to this comes from. And you might see this on a hodograph, right? This is a typical hodograph. And what I'm actually going to point you to here, as far as what we're going to be kind of focusing on, is this highlighted area, right? So remember, the hodograph is just a line plot of wind with height. And this is essentially, as we go from these kind of darker colors to the lighter colors, we're going up in height. And in this particular case, I believe this is actually a effective inflow layer, but this outlined area right here, this is the storm relative wind, or the storm relative helicity. And if you're familiar with the concept of CAPE, or convective available potential energy, right? That's the area that's enclosed between the parcel curve and the temperature curve. Well, helicity is actually a very similar idea, where it's the area between the curve created by the low bound of so in this case, the surface, we're looking at the ground, and somewhere like maybe 1.5 kilometers or so. The area enclosed between that space and the hodograph is your storm relative helicity. And they're actually both technically a measure of energy. In this case, we're looking at a kinematic energy, where when we're talking about CAPE, it's thermodynamic energy. But what we want to take away from this is that this is telling us something about spin. So you might see it on a hodograph, and then you might also see it on a plot. So this is actually coming from Weatherfront here on the right. And you notice this is just a map, and I actually believe this is for this evening. Actually, there's some decent kinematics that are going to be moving across the plains. Of course, you need to have all the thermos in place. You have to have instability. You have to have a cold front. So just because you have storm relative helicity does not mean that you're going to have tornadoes or storms or anything like that. But in this particular case, for this this evening going into tonight, there is a decent amount of shear that's going to be in place across the Central Plains. Not necessarily there's going to be a severe weather threat in that area. But as you can see, some decent storm relative helicity. So these are two ways you might actually analyze this when you're forecasting. But first, we need to talk about what it is. And I know I throw this stuff up here all the time. I promise we're not going to go too deep into the woods here. This is the actual equation for storm relative helicity. And there's a reason why I want to show you this. So essentially, storm relative helicity is going to be equal to the storm relative wind times the streamwise vorticity. And this is going to be done between some depth, 0 and 3 kilometers. So this is some calculus here. This is an integral. So essentially you could call this the storm relative helicity as being the summed product of storm relative wind and streamwise vorticity over some depth. So we're going to multiply storm relative wind times the vorticity, and we're going to do that multiple times through some depth in the atmosphere. In this case, we're looking from 0 to 3 kilometers. Okay, so what we're trying to do here is determine between some layer what the wind shear is, how the wind shear is behaving. So remember, the storm relative wind is the wind felt by the storm due to the storm's forward motion. Okay, this is what we call the storm relative wind or the storm relative inflow. Okay, so that is also how we determine what the inflow is. On the other hand, streamwise vorticity is the environmental vorticity that is pointed in the same direction as the storm relative wind. When they are pointed in the same direction, when they're aligned with each other, that means it's easier for a storm to bring in that vorticity. And if you're wondering about vorticity, that's something that's been covered quite a few times in the last few coaching sessions I've had. We've talked about surface vertical vorticity. We've talked about streamwise vorticity. We've talked about origins of updraft rotation. There's probably a couple other ones I've missed, but we've talked about vorticity and all of those. So you can, of course, go back and check those out from Storm Chaser Coaching. But essentially, the idea is that the vorticity is just the amount of spin at a point. And if you have wind really fast at some height and below that wind's a little bit slower, you're going to naturally create some spin. And if the storm can bring that spin and kind of pull it up into itself, that's how it acquires rotation. So if the direction of that spin is pointed in the same direction as the flow that storm is feeling, it's going to be easier for that storm to ingest that rotation and start to rotate itself with a rotating updraft or a mesocyclone. Okay, but the important thing about why I showed this is a tool to examine how well a storm can ingest vorticity. And the idea is that a storm that is able to ingest vorticity efficiently or effectively, the stronger its mesocyclone might become and may stay over time, right? However, you'll notice that there is storm relative wind and streamwise vorticity. This is the wind that a storm is feeling in its face. This is the amount of spin in the atmosphere. These are two different things that we're multiplying together. Okay? Take one break from that, and this is a figure here from Arkowski and Richardson 2014 that is describing how a thunderstorm might obtain its mid-level updraft. So we'll call this region right here like the main mesocyclone, but then you also might have a low-level mesocyclone down here. And you'll notice that the main updraft is going to be obtaining its rotation from the wind shear. Notice you have wind out of one direction here, and maybe it's a different direction here. And if you were to put a football in that flow, you'd create a spiral. If that spiral, which is pointed in this direction, is the same direction as this wind right here, that means this spiral of air is going to be picked up by the storm when it gets underneath the updraft and carried upwards. And now all of a sudden you have this rotating updraft in the storm. So you kind of get the point here, right? For tornadoes, it's different. And again, you can go back to the origins of supercell updraft rotation for a discussion on tornadic rotation, but that actually comes from someplace else. But again, what we're talking about here is that SRH is trying to actually tell us about this process of ingesting these football spirals of spin up into the updraft. That's what SRH is trying to tell us. Again, the problem here is that we have both storm relative wind and streamwise vorticity included in that calculation. So imagine if you have a simple equation and you're trying to make the number 10. How many different ways can you make the number 10? 10 times 1, 1 times 10, right? 5 times 2. There's multiple different ways to achieve 10. So when you're looking at that SRH number on a sounding, you might see that it's 200, for that particular SRH variable that you're looking at. But the question we want to ask is, how did we get 200? And I'm just going to make some numbers up here, right? If the first term in that equation is 10 and the second one is 1, right? That means one of our terms is really strong, but the second one isn't, right? And just because those two numbers combine to make something that looks good, that 200 SRH, does not mean that the storm is actually going to behave as if it's feeling a true 200 SRH. So let me talk about that. Again, SRH may be large, purely due to a large storm relative wind and a large streamwise vorticity, or perhaps some combination of both. However, this can be a little misleading. So this is an example. This is a map, and on this map here, we're looking at, in the black circle, we're kind of have area 1, and then in the yellow circle is area 2. And it might be hard to see here, but there's like photographs on the map, and in this kind of this darker color here, this is actually going to be the magnitude of, I believe, it's 0 to 3 kilometer storm relative helicity. And then in the filled kind of colors in the background, that is going to be the streamwise vorticity. And then in the black is the 0 to 3 kilometer storm relative wind. So we're looking at all these kind of terms here. But you'll notice that in the black circle, storm relative wind is large and the streamwise vorticity is large, so SRH is large. However, even though we have pretty similar streamwise vorticity here, the storm relative wind has gotten smaller, and so SRH also becomes smaller. So, okay, there are two pieces. What I'm trying to get at is there's two pieces here, right? And they can kind of pull on the equation in different ways. But it turns out that both of these individual components actually mean different things for storm behavior. So when we look at just the one SRH number, we actually are missing parts of the information as to what is contributing to how our storms are going to behave. Okay, so this is the takeaway. Large SRH is not always great. Small SRH is not always bad, because it depends on how you obtain that SRH based on the equation. Okay, so here's two scenarios that I want to point out. And this actually comes from Peters et al. 2020. So if you're interested in reading more about this, you can check out this paper. It's something along the lines of differentiating the contributions of streamwise vorticity and storm relative wind on supercell updraft properties, or disentangling, or something like that. So good paper, and this actually works on some idealized simulations of these individual characteristics of the wind profile, and tries to figure out, if I change the storm relative wind, what does it do to storm behavior? If I change the streamwise vorticity, what does that do? That sort of thing. So let's start with storm relative wind. What they found in this paper is that this is actually the best predictor of whether a storm will be a supercell or not. And it also might have implications on updraft size. So the example here is that larger storm relative wind can achieve wider updrafts and a higher likelihood of that storm actually becoming a supercell. On the other hand, streamwise vorticity is a better predictor of low-level updraft velocity and low-level rotation. So these two things are telling us different components of storm behavior. If you have more streamwise vorticity, you have a higher likelihood of stronger low-level rotation and stronger updraft strength. Okay? Different parts of storm behavior. We're talking on the top with storm relative wind, is it even a supercell? And on the bottom, are we able to see rotation right down near the ground, right? Very different things. So, for example, if streamwise vorticity is 10 and storm relative wind is 1, going back to that original equation example, sure, we have all kinds of streamwise vorticity and our SRH still looks good, but at the end of the day, maybe we don't have enough storm relative wind to even get a supercell in the first place, right? So hopefully that's starting to make a little bit more sense there. Now, of course, we still want to look at SRH. This is not necessarily me saying, oh, let's quit using SRH, right? We just have to learn to use it the right way. And sometimes the best way to do it is actually looking at the components independently, individually, looking at both terms of the equation. So this is going to be a few examples of what you might experience in the real world. So maybe we have a small, low-level storm relative wind. So maybe we're looking at the lowest 1 kilometer, lowest 3 kilometers or something. And it's maybe something like 18 to 22 knots, just made something up here. Typically, when I see this, I consider that a small value. And maybe streamwise vorticity is actually kind of large, 0.03. We're getting up there. This is pretty good. A lot of our bigger days are pushing that threshold. And we'll talk about this more in just a little bit here, but typically when we have smaller storm relative wind, we're more on the low precipitation or LP side of the supercell spectrum. And then when you get your storm relative wind closer to like 30 and 40, that's when we might be talking more of either long-lived supercells or more HP supercells. Can also happen with larger storm relative wind. And by the way, this is per second. So this is per second. Rotation is per second. So in this particular example, maybe we expect low precipitation supercells with strong low level rotation because maybe we have just enough storm relative wind to get a supercell, but it's probably going to be low P or low precipitation. And then eventually, if we do get that supercell to form, maybe it will have a chance at low level updraft rotation. However, in this case, storm relative helicity might be rather small because the storm relative wind is small, yet we might still have tornadic supercells in this particular example. Now, another example could be a large storm relative wind, 35 to 40 knots. We typically see this a lot in the southeast with our big southeast synoptic days in early spring. And streamwise vorticity could be small in this case, and this still isn't terribly small. This is a relatively decent value, but in this case, maybe you expect a classic or maybe high precipitation supercell, depending on where you are. Of course, thermodynamics also play a role in this, but we're just pretending that those don't exist for the sake of this conversation here. But perhaps in this case, we're looking at supercells, but maybe they just don't have enough of this rotation in the atmosphere to actually obtain low-level rotation. So SRH in this case might be somewhat large because we have such large storm relative wind, but we might not actually experience the supercell behavior we'd expect from that large storm relative helicity. Okay. So next I want to share some values, some typical values. And this is just, there's no set research that has shown this. This is kind of based on my experience and what I like to look for. And so these are values of storm relative wind, streamwise vorticity, and then the overall SRH. And if it's very weak, moderate, strong, or very strong. So typically, and this might be over the 0 to 3 kilometer. I guess I forgot to write this down. This would be like over the 0 to 3 kilometer layer. That you kind of be looking for something like this. I really like to see my storm relative wind pushing the 30 knots mark. You can get decent supercells that are tornadic anywhere in this range. I've found you don't always have to have the high end for stream or for the vorticity, and that is because you can obtain vorticity in other ways, and we've talked about that in a few other past coaching presentations as well. And then SRH. Take this column here with a grain of salt because SRH doesn't always have to be that good. There are plenty of cases where we've had tornadoes, especially on the high plains, where SRH in the lower levels might be 50, might be less than 100, right? And so we're still obtaining tornadoes, and it only takes one tornado to hit one house for this to be like an impactful event, right? And so trying to assign storm relative helicity values to tornadoes or damage or impact is very difficult to do because there's such a wide range of opportunities. But when you get into places like the southeast and some of our stronger synoptic events, usually you're pushing this 300 to 400 plus, and there are definitely cases where we're pushing 600, 700 SRH in some environments. And if you actually play around on SRH maps, especially when we get into the synoptic season, if you will, which is, winter into the spring, anytime we have really, really strong low pressure systems, you'll have gigantic SRH. And it's kind of funny, a lot of times north of the warm front, you can actually end up with SRH values well over 1,000. Of course, it's north of the warm front, so it's not really gonna be any impact as far as severe weather is concerned, but you can get some pretty large storm relative helicity values in the atmosphere, typically for severe weather setups. So we're usually in the order of 100 or a few hundred. So I want to share some examples and kind of where to find this. So this is a sounding plot here. This is actually a model reanalysis. This is coming from the April 27, 2011 outbreak. So this is near Tuscaloosa, Alabama. this is a really nice hodograph, right? You've got very large low-level curvature here. And of course, when you have a very elongated hodograph, you have large storm relative wind. And I'll just draw the storm relative wind on here for you real quick so you can kind of visualize this. The storm relative wind is going to come from this guy right here. This is telling me where a right-moving supercell is going to move to. It's going to move to the northeast, and we just figure out where this is on the plot. So we're somewhere 45, 50 knots-ish for that motion. And then we just draw that, we draw a line from that point back to the hodograph, and this tells us what our storm relative wind is. And so in this case, we're pushing something like, this is probably around 45. So it's probably about 45 knots there in the lowest half kilometer. And I was pretty close. It's about 42 knots here. And so this right here, this is a sounder pi sounding. And what you'll find here on this particular sounding is that these parameters are actually broken down. And you have the bulk wind difference, which is not a component of SRH. But you have the SRH value, you have the storm relative wind, and over here you actually have the magnitude of streamwise vorticity. So we can independently analyze each of these parameters. And you can find this in other places. This is weather front, which is actually also a sounder pi sounding, but you'll notice that we have the same bulk wind difference, the SRH, and the streamwise vorticity magnitudes in this little box of kinematics down here. And so this is actually one of the profiles from that first SRH map that I showed in one of the first slides for tonight, I believe. Yeah, so Tuesday at 22Z, which is about an hour ago. So this is just plucked in the middle, and because you have this kind of very curved hodograph, you've got a lot of streamwise vorticity in here technically, so you've got a decent amount of SRH associated with this. Once you get up into this like 0 to 3 kilometer layer, you can see we're pushing 600 for the 0 to 3 kilometer SRH. But you also can look right here, right? We've got 32 knots for the storm relative wind. We also are pushing that 0.01 per second for the magnitude of streamwise vorticity. So this is decent, right? We're able to obtain storm relative wind here. You can also find this on SounderPi. So I just showed this example here. This is from a different example, different case, and you can see that box down here. Of course, you can also visualize this just by looking at the hodograph, right? So if our hodograph looks something like this, and we might have a right mover point here, right? You can draw the vectors and kind of figure out the magnitude of storm relative wind, and then you can also tell I'll do a quick demonstration of streamwise vorticity. If you take a segment of your hodograph and draw a line perpendicular to that, that is the vorticity vector. So you'll notice in this case, if I were to kind of transpose the storm relative wind vector on here, they point in similar directions, but not a perfect direction. So this is not a perfect alignment. So this is a almost streamwise case. So you'd say a majority of this is streamwise, plus there's a lot of storm relative wind, so maybe we have a lot of SRH here, right? So that's kind of a very quick back of the napkin kind of SRH example from looking at the hodograph. Now, and then of course that's highlighted there. I do want to add a few kind of points here for you as we part this quick little demonstration of SRH, and then some tips for using it from a forecast perspective. So I definitely think that when you're looking at this, it's okay to look at soundings. It's okay to look at maps. Soundings are going to be the best tool to look at those two components individually. That's why we put so much emphasis on looking at the hodograph, and there's plenty of hodograph technique videos that have been shared on here. But when it comes to looking at SRH from a forecasting perspective, you just want to analyze, do we have directional wind speed or directional wind shear and some kind of speed shear, right? The more speed shear we have, the more directional shear we have, generally the larger our SRH is going to be, right? So that's from a very basic perspective. Typically, fast storm motions will have a larger storm relative wind and thus larger storm relative helicity, and that's because that little RM, that right mover we were looking at, ends up further away from the origin, which means it's further from the hodograph. And so you typically have a larger storm relative wind there. And that's why in the southeast, we typically have very large storm relative wind environments, because those storms are moving so fast because the wind shear is so strong. Number 3 is a big one. So this is actually kind of interesting. And this could be a whole topic for a different different talk here, but the storm relativity will actually strengthen during the evening and into the overnight hours as the boundary layer starts to decouple. Okay, so imagine you have a sounding that might look like this. So this is our temperature profile throughout the day, and this right here is going to be the top of the atmosphere here. And so during the day we warm up, and so our temperature line is kind of pushed to the right. But once we start cooling off in the evening, and I'll say this is what it looks like at a later time, our temperature might actually do this instead. And so what that means is now our temperature is kind of cooling, so it's going back to the left. When that happens, we actually we create an inversion, and air does not mix between the inversion. So what that means is the bottom part of the this layer that has really strong flow essentially has no more friction, so it actually gets faster. When that happens, we see the low-level jet intensification. That's why the low-level jet intensifies, actually. And then when the low-level jet intensifies, SRH will also start to strengthen. SRH is not rare, large SRH, when we have really large SRH. But typically, what happens is it's difficult to get really large SRH at the right timing with the forcing mechanism and sufficient instability and favorable storm mode and all that stuff. Getting all that stuff combined can be a little bit difficult to do. So it's more common that you'll see SRH on the order of about 200 or less. And again, the big parting thing here is that small SRH is not always a bad thing. Supercells can still become tornadic with poor kinematic configurations, and that is why it's important to consider other components of the environment when you're forecasting for severe storms, when you're forecasting for your chasing, because there are multiple different ways by which we can obtain rotation, especially at the ground. For example, we talked about surface vertical vorticity on one of my last coaching sessions, and so that's a way that we can do that, which has no SRH has no implication on that. But in this case, when you're looking at something like storm relative helicity, break out into terms, look at the two different components. You can do that by looking at the hodograph, and look around. You'll find some examples where on some days you actually have really large SRH, but the hodographs still look funky. Maybe it's just being dominated by really strong storm relative wind or something like that. So, Gabe, I think that's all I got for you here. I was trying not to take this take like 4 hours here discussing this, but I'll be happy to take any questions at this point, and hopefully that was useful in everybody's interpretation of SRH.
Kyle, that was absolutely incredible because I never actually put the two and two together about how, with the SRH parameter being composed of those two separate quantities, it really matters if it's 9/10 one part and 1/10 the other versus the other way around, and how that can drastically change what your expectations should be given which parameter is dominant, or if they're both in there equally. And it's kind of like a game within a game, so to speak. You see that there's SRH, and you got to break it down and look at a bunch of different other stuff to determine what that actually means.
Well, we can take that one step further, and this is getting into the other thing here. Supercell composite and significant tornado parameter, SRH, is a variable in those equations as well. So in when it comes to like high level like dynamics and really into the weeds of meteorology, we like to take things back to first principles, right? Is the flow turning, that sort of thing. But when you get into something like the SIGTOR or supercell composite, we're taking SRH, and then you have to take SRH back out, and then there's two things inside of that which are also technically not first principle parameters. So like we're kind of taking a definition and then like folding it over a few times, kind of origamiing it into something totally different by the time it ends up in the significant tornado parameter and SCP. So that's one of my problems with parameters like that, is because we start folding so many things into them, it gets difficult to interpret what they actually mean and why. But yeah, an SRH is kind of a smaller example of that, and looking at those two terms is important.
And I apologize, JM, for the double ping over in the general chat. I was using you as a guinea pig for a couple of changes that I made to one of our automations. So we'll go ahead and open up the floor. I know people have lots of questions here, so we're going to dive right into it. And I'm going to start off with YouTube because that is, of course, the newest addition to our live stream component. And as a reminder, you do have to be a channel member to get your question asked live on air, but there are some questions that are in the chat right now over on YouTube that are actually more administrative in nature. So I'm going to shout you guys out and answer those right now. But if it's a meteorological question, you will have to become a channel member. $3 a month. Just click that join button right below the video. And that counts for, by the way, all live streams. So we do 2 live streams at least every single week on average. So that's 8 total live streams per month, sometimes more. $3 a month gets you access to unlimited questions on all of our live streams, as well as our Discord server, which has a Q&A chat that you can access anytime. Our coaches pop in and out. They answer your questions whenever they have availability. So Juan C. Astaneda says, sorry for not asking sooner, but will this stream be made available on the channel after it's over? Yes, great question, Juan. So all the live streams are in a public playlist. The big live stream with all of the back and forth that Kyle and I do and all the questions and all that other stuff. What won't be available afterwards is the super streamlined presentation where we take Kyle's talk on SRH, we edit it up really tightly so that it's a really nice presentation that you can have access to, and you can reference it if you need to. That is part of the $3 and becoming a Chaser Academy member. So if you want access to that, that's something you'll have to do. But the big live stream, the thing you're watching right now, that's available right afterwards. Radar and Reason says, for the content manager position, which, by the way, we are hiring for a content manager right now. There's emails that have went out about it. There's stuff in our Discord server. There's a community post on YouTube. So Discord, go to the announcements, or you can just find one of the tweets on Twitter. They want to know, is there a requirement, age, location? Got to be 18 plus. Just don't want to run afoul of any labor laws anywhere. I don't even know what you have to do if you're under 18, but I don't want to mess with any of that. And then location, it's all remote. So as long as you have a working, strong internet connection, you will be good to go. And then the last 2 questions here from Radar and Reason and Lana to Kim. Let's see. I'm hoping, I guess I need somebody to be able to look and tell me, are these guys channel members? Because if they are, I definitely want to ask the question, but if they're not, you guys will have to click that join button. So give me just a second. You guys on YouTube, I'm going to look into that while Kyle's answering the next question. Radar and Reason and Lanita Kim, hang on there. Going over to Discord, though, we've got some good questions to start off with. So Jen Shark, first of all, wants to know, Kyle, could you please link the paper in the chat?
Oh, yeah, definitely. I can do that. What would be the best place to do that, Gabe?
So if you link it in the chat and then also send it to our stream technician, Tyler, over on our Telegram chat, he can add it to the description of the actual video once we're done streaming.
Okay. Yeah, I can do that.
So that'll be down there for anybody. Off topic, says Nebraska Chaser. A lot of off topic stuff. That's speaking my love language, guys. I love off topic. Nebraska Chaser wants to know, do we have a Dr. Gillett yet?
No, okay, that's a funny question. No, so I will be graduating with my master's actually on this Friday, and then I will be starting the process of eventually becoming doctor in 2 weeks. So it'll take a few years. It'll be a while till I get to that point, but one step closer. So thanks for asking.
Dr. Kyle Gillett. I cannot wait. I'm excited.
We're getting there.
Greenie Boy. What up, Greenie Boy? Question is kind of specific, he says. So I want to come up on stage. Wait, I can't. Never mind. Yeah, sorry, guys. We can't do the on-stage stuff anymore. But Greenie, okay, I see you tossed your question in chat, so I'll do it right now. In regards to SRH, I tend to notice that curvature doesn't always matter. Take example, this photograph from the 2021 Ida tropical outbreak. Kyle, what would be the best place to send you a picture of this photograph?
Can I see it in that chat, or because I'm trying to...
Yeah, if you go into the questions channel, the Ask Questions Here chat, you'll be able to see it. But I can send it to you whatever you have pulled up, so you're not trying to jump from place to place.
I think I found the questions chat.
It's the very bottom question.
Yeah, I got it. Yep, I see it.
Okay, so I'll finish asking the question, and you can take a look at that while I'm reading it.
Yep.
All right. So take for example, so in regards to SRH, I tend to notice that curvature doesn't always matter. Take for example this photograph from the 2021 Ida tropical outbreak, where the low levels don't make a full low level hook curve. I tend to notice that when your surface to 1 kilometer HODO is kind of straight, where the 2 to 3 kilometers will start to curve, is when you get really good environments for tornadoes. I wish I could explain this better. And I'm going to go ahead
Yeah.
and real quick. I'm going to go ahead and forward that to people that are actually in the chat. That way, you guys can take a look at what he's talking about.
Yeah. So, I mean, this is a good question. And so there's a lot of nuance here. In my experience, in my opinion, there is no one right way to make a kinematic profile or one way to make a photograph that is going to be favorable for tornadoes. I'm a firm believer that the environment is only half the problem and the storm is the other half, and it's going to do the rest of the work. In some cases, it's more than half or less than half. But so what I'm trying to get at here is that as long as you get a supercell, the storm will pick up the rest in some cases, pick up the rest of the slack. And so when I say that, what I'm trying to get at is essentially in this case, this photograph might have worked, but in another case, it might not have. In another case, a more curved low level photograph might have worked. In another case, that same setup might not have worked. And so I try not to get too into the weeds on that. But in this particular case, yeah, it's not terribly well curved in the lowest levels. However, this photograph is almost entirely a circle. If we went up a little bit higher, it would pretty much look like a circle there. And I'm looking at the SRH values here. You have such large storm relative helicity, and this is an excellent example of this, by the way. This is perfect. This is exactly what I was trying to get at before. You said there's not a lot of low-level curvature. Low-level curvature is how you get streamwise vorticity. So when you don't have that, right, but you still have huge storm relative helicity for the lowest 500 meters, right? 300 in just the lowest 500 meters of that profile. And for anyone that's not too familiar with SRH, before we're talking about 0 to 3, kilometers, which is 0 to 3,000 meters. And we were like, oh yeah, 300 is a good number. No, this is 300 in the lowest 500 meters. That's huge, but when you actually look at this profile, this is purely because of the storm relative wind. There's not a lot of curvature, so there's not a lot of vorticity here, but there is a huge storm relative wind. I don't know if it tells me what the storm motion is 46 knots. And so at the surface, the storm relative inflow is 46 knots. So that's a perfect example of the storm relative wind carrying or dominating the storm relative helicity terms, such that this helicity is huge. So that's an excellent example. In my case, or my example that I was sharing before about how in some cases, this might look good, or in other cases it might not. What I'll say about this is my requirement for a chase day is that we have the kinematics to get a supercell. Once we get that, which large storm relative wind can do, I'd like to see the storm picking up the rest of the slack, if that makes sense. So in some cases, when you're saying, yeah, maybe we don't need as much low level curvature, yeah, there's definitely cases where that's true. If you look at the high plains in June and July, there's a lot of days where there's not a lot of low level curvature, but there's enough of everything else to get a supercell, and that might be the case here. Of course, TC tours are a whole nother ball game as well, but yeah, that's an excellent example.
Appreciate that, Kyle. And I did confirm by sending a test question from my own personal YouTube account that you got to have the little badge. So it turns your name blue, or at least whatever color your badge is. I don't know if everybody's blue, but it turns your name a color instead of the normal gray shade. And you get that little star badge next to your name if you're a channel member. So Lanita Kim and Radar and Reason, happy to answer both of your questions if either of you join and become a member of the channel. But other than that, we got to save the questions since we have limited time for the channel members. So really appreciate, though, both of you hanging out here, being a part of the live stream. That goes for everyone on Discord as well if you can't ask questions. Appreciate you being here and just joining the conversation. You guys are what make all of this special. So let's go ahead and get to some other questions here, Kyle. Nebraska, nope, sorry, that was asking about Dr. Gillett. JM, Sanus Northeast Chaser. Hello, Kyle. He says ominously.
Here we go.
I have seen some references saying 0 to 1 kilometer BWD,
Yep, bulk
is
wind
that bulk wind
difference.
difference, okay,
Yep, yep.
is also a good parameter to quickly look at for discriminating tornado environments. It makes sense as long as you sanity check it, make sure you have a strong concentration of vorticity in the low levels, and your SRH isn't going to be entirely driven by SRI. So, what do you think about that statement?
Yeah, so I'll just explain some of these acronyms here. So BWD, that is bulk wind difference, and that is just essentially it's the amount of wind shear difference between two layers. So that's just the wind shear, the speed shear between two layers, more or less. You can think of it that way. And in this case, he's asking about 0 to 1, and then of course we have SRH and SRI. Remember, storm relative inflow. Yeah, again, this theoretically, the more low level storm relative or larger wind shear you have in the lower levels, the more likely it is that you're going to have large storm relative vorticity. Because if you have really, really strong wind shear, especially at the ground, remember that the ground is going to provide friction, which means the wind right at the ground is going to be significantly slower than the wind right above it. And that's going to help you create vorticity. Of course, that also still has to be ingested up into the storm. So it's not, sort of plug and chug kind of thing. But in my experience, I don't look a lot at 0 to 1 kilometer bulk wind difference. I'm more oriented for upper levels, mid levels, for the kind of just bulk wind shear. And you might see this again, if you're not familiar with the acronyms, you might see it labeled bulk wind difference. You might see it labeled as BS for bulk shear, that sort of thing. But yeah, that's possible because you're able to create more low level vorticity when you have stronger low level wind shear. So yeah, I would say that it could be a way to discriminate between tornadic and non-tornadic environments. But like you said, right, there's a bunch of other components to the context for when you're looking at that sort of thing.
And Kyle, real quick, I noticed your screen share is actually still up. I didn't catch that until now, so you could probably go ahead and cut that out. That way
Oh,
they can
okay.
see our big, beautiful faces on the screen
Oh
as we
no,
answer their questions.
I don't know if that's a good thing.
And I actually am really happy that you mentioned that BS means bulk shear because people all the time, my whole life, have been telling me to cut out the BS. I had no
Yeah,
clue what they were talking about. Now I know they were telling me to stop with the bulk shear. So,
yeah, they just don't want their houses to be hailed on and or hit by tornadoes or anything. So that's all they meant.
which is perfectly reasonable. So I
Yeah,
totally get it, guys.
right.
I'll definitely watch the BS from here on out.
There you go.
All right. Next, I don't know why you coaches put up with me, by the way. But anyways, let's move on to next question. Kazaki Senju, I think I pronounced that right. Usually, I'm not bold enough to go for last names. I don't know why I just read that, but Kazaki asks, "What is the perk of using SRH instead of just using SRW and SRV separately?" As I have heard conflicting points of view on using SRH versus the other one being more reliable.
Yeah, SRH. So the thing that we like to do as forecasters is make things quick and easy. We like one-stop shops, right? That's why we like Weatherfront, right? But SRH, supercell composite, significant tornado, any of your favorite composite parameters, those are all ways to do one-stop shop, ways to analyze the environment. And that's what SRH is. It's trying to take two parameters that we know are important for supercell rotation, smash them together, put them on one map, one number on a sounding, and then hopefully that's going to give us some insight. And if you were to use it strictly as are we going to see rotating storms today and look at SRH, it's a good parameter. And that's kind of how I started this presentation. It works. But if you want to understand a little bit more about how the storms are going to behave, which is especially true from a chase perspective, right? As I started out saying, I'm a photographer. That's what I do when I chase. And so I want a good looking storm. I want photogenic tornadoes. And so I want to know more about how the storm behaves to make the chase worth it for me. It's going to be different for everybody else. But looking at these things in more detail is going to be more important when you're trying to get more information about how the storm behaves. So if you're doing a quick look, SRH is excellent. That's exactly what it's designed for. But if you want to understand more about how the storm is going to behave and how it might evolve and the hazards that it might have, we have to start kind of peering behind the curtains and going into a little bit more detail.
Next question on the list is coming in hot from JM. Let me make sure this isn't just a follow up to what he was asking about earlier. Yeah, JM says, I don't know if it's okay to ask about since it's not super related. Absolutely. You can ask any question you'd like. He wants to know, where do severe downdraft winds come from in cold season events?
Mm-hmm.
For forecasting wind bags, I'm used to looking at scuties with strong evaporative
Mm-hmm.
cooling potential, inverted V, loaded gun, depending on where the downdraft starts, as well as high decape and PWatt.
Yep.
But for cold season events, you don't have much of that at all. I considered mesovortices, but thinking about, say, March 16th from this year, there were definitely mesovortices, but I don't think every wind report came from a mesovortex. So a lot of stuff again to unpack there. JM is stretching the mind here tonight
Yeah.
with some great questions.
No, that's a good question. Yeah, and there's actually a fairly simple answer. And if you look at a sounding in the cold season, because the cold season typically has stronger synoptics, because the warm air is further to the south, cold air is further to the south, and so we have this kind of more stark battle between cold and warm air, just in general across the hemisphere. And so when that happens, we increase the jet, and so our lows are stronger. The low level jets are typically stronger, so we just have more wind ambiently in the environment. And so imagine that maybe you have the ground, and then above the ground you've got some wind that's moving 50 knots or whatever, and then suddenly you drop a downdraft on it. That downdraft is going to grab onto that flow that's higher above the ground and drop it down towards the surface. And so you're right that in the summer a lot of that's being driven by evaporative cooling, which makes the air more dense. As that air becomes more dense and cooler, it falls faster, so you have a stronger momentum transport down towards the ground. But in the case of the cool season, especially if you're in like the months of March, or this happens a lot in like October when we start getting these fall events in the Northeast, or we get this a lot in the Great Lakes in the Midwest. A lot of what these environments are just really, really strong wind shear environments that are in these kind of linear systems, and there might not even be any lightning, but they're all severe warned because of wind, and that is because we're actually taking these downdrafts that are pulling down those stronger winds from aloft down to the surface. And so it's another form of momentum transport. And you are correct that mesovortices, these areas, and this is actually some new work that's being done here at the University of North Dakota to kind of look at some of this, but mesovortices are a way by which we can locally intensify the straight line winds associated with these linear systems. Because imagine you have the linear system that's moving along and it has its wind associated with it, and then suddenly you have this little area of flow that's kind of kicking out, and you end up with that kind of kink in the line, and then we're creating stronger winds there. But yeah, definitely transport of stronger horizontal winds aloft down to the surface in the cold season.
All right, and folks, I'm going to go ahead and call it the cutoff point now for questions. So I'll give you like 60 more seconds if you can get your question in either on YouTube or on Discord. But we're going to try to keep these to an hour most of the time since we are doing them twice a week. We're also doing forecast shows whenever there's a 2% tornado probability anywhere in the country or higher. So we are busy little bees these days. And as such, we're going to try to limit these to an hour if possible. On YouTube, I see we've got another wonderful question that came in from TDMB or TDMBT. So just a reminder over on YouTube, if you're not a channel member, then we won't be able to answer your questions on air. Again, we've got limited time. But if any of you who have asked a question and you're watching on YouTube want to click that button, support us for $3 a month, that gives you access to questions anytime that we do a live stream. So next up, we have Kazaki, once again, with a great question. I know there is 0 to 1 kilometer and 0 to 3 kilometer for SRH. Is there one level in particular that you want to focus on more when it comes to tornado genesis? Or are both levels important when it comes to that?
Yeah, I mean, both levels are kind of important because typically not always the case, but in most cases, to obtain a tornadic behavior, you have to be a supercell in the first place. At least to be most successful as a chaser, that's the type of tornado you're going to be looking for, is our supercellular tornadoes. So 0 to 3 is going to be the best for seeing, are we going to have supercell behaviors today? Of course, you still want to look at those individual components, right? But 0 to 3 is typically best for the supercell part of the problem, and then for the tornado genesis part of the problem, yeah, 0 to 1 kilometers is going to to be better. Anything closer to the ground. Sounder Pine Weatherfront, you'll also find 0 to 500. And tornadoes are typically going to be 0 to 500 meters tall. Some other papers have defined 0 to 300 meters tall, or at least the part of the tornadoes we care about for forecasting. So the lower down you can get into the atmosphere is going to be better when you're talking about the tornado genesis problem. So yeah, 0 to 1 kilometers is definitely going to be better if you're looking into whether or not a particular storm might be capable of producing tornadoes.
All right, moving along here. Greeny Boy says, "Okay, Kyle." Another ominous way to start off a question. Okay,
Yeah, gosh,
comma,
guys.
Kyle. Jeez. I think you talked about this before, but on June 22nd, in the case you want to look at since it's a remarkable day, the Mid-Atlantic had a ton of fantastic photogenic supercells. One thing I noted on a large wall cloud was some very strong rolling motion on the tail cloud. Does that have anything to do with the relative inflow or vorticity?
Yes, excellent question. So if by rolling, I'm going to assume that by rolling you mean that like the wall cloud's over here on one side and you're watching the tail cloud kind of do this as it kind of is ingested into the wall cloud. And it looks like that might be what I'm seeing here from your picture. Yeah, so what you are actually observing there is a channel of vorticity that's being generated. We call it baroclinic generation between the warm air that's going to be kind of behind you in this picture, moving up towards the storm, and the cool air that's coming out of the storm. When those warm and cool air masses meet, you have the buoyant air that's rising and less buoyant air that is sinking in those two air masses. That creates this area of spin, and then the storm has inflow, right? So it's going to start pulling on that area of spin, and that gets ingested into the updraft. What you are visualizing there is more than likely at least a component of the streamwise vorticity current, or SVC, if you've ever heard of that. The SVC, the streamwise vorticity current, is a current of vorticity that's being generated internally in the storm because of these differences between updrafts and downdrafts. Updraft latches onto it, picks it up, brings it in, and that's how you're obtaining your rotation, is from that streamwise vorticity current. So that's pretty cool. I always love it when you can't always visualize that. Sometimes you don't see it clearly in the field, but it's always really fun when you can actually see that happening.
All right. It looks like the last question we have here. Let me check and just make sure that's not a lie. Yeah, it looks like between the two platforms, this will be the final question of the evening. Sanus Northeast Chaser asks, a few weeks ago, I came across a theory that I came to a theory, I think this is his own internal formulation, that higher 3-cape / low-level buoyancy could lead to smaller updrafts because stronger stretching would lead to horizontal convergence to compensate. The only example I have of this is the Moore 2013 inflow channel getting clogged, as the rain-cooled parcels would be less buoyant. The mesocyclone would relax, leading to a rapid inflation of the mesocyclone / tornado size. Once the rain cleared out, the circulation rapidly tightened back up again and promptly produced EF5 damage. So another really, really cool thought experiment. What do you think about that?
I'm gonna read this one more time here.
Okay, well, yeah, while you're reading that, I'll do a couple of pieces of housekeeping here. Want to thank all of you folks who hung out with us tonight on Discord and hung out on YouTube, and all the people, especially, who interacted with us on YouTube by asking a question. Apologies to the ones whose questions I couldn't answer. Again, channel members, just because we have such limited time, if we opened up questions to everybody, we'd be asking Kyle to stay here till like 9, 10, 11 o'clock at night, which unfortunately we can't do. I wish we could. If there was a way to actually chain up, yeah, if there was a way to chain all of our coaches to the radiator and just down in the basement and just force them to answer questions nonstop, believe you guys, like I would do it. It would be on my list of things to do, but we can't, unfortunately. So, Kyle, what do you think about that question now?
Yeah, I'll start off by saying I don't think anyone's actually like really looked at updraft size relative to low level instability. I guess my answer here would be that more than likely the idea about the updrafts becoming smaller because of stronger stretching is not necessary. Those two ideas aren't necessarily related. The updraft is just we have a increase in rising motion, and that rising motion, condensates. We have an updraft. The whole thing starts to organize, and then we have this updraft. Um, I the one thing I would caution here is that the environment. I kind of said this before too. The environment gets you so far, and then the storm starts picking up the slack and doing the other components here. So sometimes once you get a storm, how else put this is that like individual parameters are not as important as they were before you got the storm. Okay, so in the case of, well, you're talking about more here, right? And what you might be observing here with this like inflow channel and the rain cooled air and all that, you're observing different RFD surges, and those RFD surges are going to modulate low level updraft behavior and tornado behavior because of the less buoyant air, as you had observed here. And so these less buoyant parcels, they're harder to rise, and they are, because they're less buoyant, they're more dense, that sort of thing. So that would limit your low level mesocyclone strength or your intensity, and it can modulate tornado intensity for a time. There's actually a really nice paper about this following some Twistex observations. This is Lee and Finley 2016, I think. It's tornado speed and heading changes or something like that, following intense RFD surges or something. Those are actually my two advisors. But yeah, so those RFD surges are kind of what you're observing here with this Moore case, I believe. But I don't really know that higher 3 Cape will give you smaller updrafts, because there's other things that modulate updraft size, and it's actually been found in a lot of cases that LCL height and your storm relative wind are actually some of the better identifiers of updraft width. So the more storm relative wind you have and the higher your LCL are, the larger your updrafts generally are, and the stronger your updrafts can be. I don't know if there's been any look into that as far as 3 Cape. 3 Cape is essentially just, what potential buoyancy do we have in some layer, and that's just telling us essentially how fast the air is going to rise, not necessarily what the shape or dimensions of that updraft might be. In the case of stretching, yes, you do have stronger stretching when you have stronger low-level instability, but when you're talking about vorticity or stretching, you're looking at vorticity, that's spin, which is not necessarily related to the updraft. That spin goes up into the updraft, but those two things don't control each other, so to speak. Yeah, I would say I'm not sure about 3 Cape and its impact on updrafts, but that work has not been done to my knowledge. So somebody would actually have to, look into that, do some sensitivity studies, and figure out whether or not that's a relationship that exists. But that's a great question, though.
Kyle, the casual name dropping was not lost on me. Those are my advisors, by the way. Like,
Yeah,
that's how
fun.
you know we got the heavy hitters here at SEC, folks. Just
Yeah.
oh yeah, I know that guy. I studied under him for a couple of semesters.
Yeah.
No
Yep.
big deal.
Yep.
Whatever. Just happens in these parts. So
Makes my life a little bit easier, that's for sure.
all right, folks. Well, thank you everyone on Discord and on YouTube. I want to give especially a big thank you to everyone who has stuck with us during that transition period where we started off just on Discord and then we have been building out onto YouTube. It has definitely had some rough patches getting used to the new method of doing things. Stuff has broken on occasion, especially for the folks on Discord. So just want to say very appreciative of all of you. I feel like today's stream was probably the first one that has went off without zero issues. I feel like we've got all of those taken care of now. So I'm looking forward to being able to just absolutely take off just light speed into the future here at SEC. We've got a lot of awesome other stuff planned. And I also want to drop one more reminder to folks that we do have a forecast show that we try to put out anytime that there is at least a 2% tornado probability or higher anywhere in the country. If you like the discussion we get into on these live streams, you are going to love what some of our coaches like Kyle, Hunter Fowkes, Cameron Nixon, what those guys, Stephen Cross, get into during their shows. Kyle's last one was what was it, a 49-minute marathon where,
God.
dude, it was like a college
too
level
long.
course.
It's too long.
You know what? It might have been too long, but it was beautiful because it was like I was listening to a professor that I didn't have to pay tuition to hear, and it was incredible.
Okay.
So, all
Very
right.
good.
So thank you again, everybody. And yeah, we will see you for the next one tomorrow night, I believe, is Office Hours with Trey Greenwood. Phil Johnson from Stormfront Freaks will be the host for that one. So that is a completely free show as well. And same rigmarole as tonight. If you want to ask questions, you'll have to be a Chaser Academy member. And if you just want to hang out, watch the show, talk with everybody in chat, feel free to join. We look forward to seeing you there. Take care, folks.
See you guys.